Hello and welcome to today's webcast, Veritas NetBackup Tuning Tips, brought to you by DataLink and Insight Company. I'm Amanda Sharp, Marketing Admin at DataLink, and will be your moderator today. Before we begin, I wanted to cover a few housekeeping items. This webcast is designed to be interactive between you and the presenters. The webcast console you are looking at can be completely customized. You can resize or move any of the windows that you have open. If you have any questions during the webcast, you can click on the Q&A widget at the bottom and submit your question. All questions from this webcast will be captured. If you are experiencing any technical difficulties, please visit the webcast help guide by clicking on the question mark icon below the presentation window. The help guide covers common technical issues. I would now like to turn this presentation over to our presenter, Chette Boardman. Chette, the floor is yours.
Thank you, Amanda. Welcome, everyone, to this month's Tech Tuesday. I'm glad you joined us today. I think this is going to be a really good presentation. If you have any questions during the presentation, please feel free to put those questions in, and we will get them answered for you. Today, we're going to cover NetBackup tuning. We're going to cover some appliance-specific and some traditional NetBackup installation-specific items as well. We're going to start off with covering some touch files. We'll move into how to adjust those touch files, values, where they're placed. We'll then move into buffering. We'll dig into how the buffering works and how data moves from client to media server and finally to storage. We'll cover some multiplexing, multi-streaming. Then we'll dig into the appliance stuff, and then we'll move into some of the considerations that you'll want to take into account. And then we'll move on to the testing performance. There's several different testing methodologies to kind of pinpoint where your problems are coming up. And we'll address common issues and solutions. And then we'll finish up with any questions that have not been answered. We'll address those. So with that, let's go ahead and get started. So NetBackup is probably the most network-intensive application for backups that you will run into. The unaltered NetBackup, base install without throttles or customization, will use 100% of the resources available to it. So it does not intelligently use 70% of your network. It attempts to use all available resources to move the data as fast as possible. And that's one of the things that will really test an environment when you're pushing your network, you're pushing your servers, and all of the hardware in between to its limits. NetBackup is very good at doing that for you. So one of the things that NetBackup is not good at, and it is getting better, is the network connectivity. If network connectivity is lost, backup jobs will fail. There is resilient networking that has been added into recent versions of NetBackup that help to make it a little bit more tolerant of network issues, but large-scale network issues will cause backups to fail. This is almost a guarantee. And one thing that will guarantee job failure will be packet loss. If your network is experiencing packet loss outside of the normal retransmissions in the lower layer of the OSI, your job is going to fail. It's a very complex product involving a lot of processes that talk to each other through the network. Even local processes will talk to other local processes through the network. So your network is the biggest linchpin for backups to be successful. Typical signs of issues, and we're addressing tuning here, so one of the biggest things you're going to see is that your performance is not what you'd expect it to be, or it's degraded for some reason. And some of the signs you'll see are very high client or media server timeout values in your configuration, having to continuously up those to keep your backups from failing. Those are signs that you may have performance tuning may help you there, or you may have network issues, and we'll cover a lot of that in this presentation. So let's start off with the touch files. NetBackup behavior can be altered by touch files, and these are typically either files that have no data in them, the name just exists, or there are values within the file that are read in that adjust how NetBackup moves data. starting with the master server settings that you can alter in the GUI will be your max jobs per client, max IO streams, max jobs per policy, VMware, and Hyper-V throttles. These are going to be within the GUI that you can alter how many streams of data from a client, how many streams to go to a specific disk pool, how many jobs you want to go active from a specific policy if you're attempting to load balance across policies. VMware throttles and Hyper-V throttles, these will throttle things like data stores, the number of streams from data stores, and number of streams off a specific ESX host or Hyper-V host. Media server touch files. These are what control how data is moved in terms of size. So the first one is going to be size data buffers. And we'll cover how these buffers come into play in an upcoming slide. But the size data buffers is probably one of the biggest adjustments that you can make. And there's two different files you'll notice here, size data buffers and then size data buffers disk. And the difference between the two is that disk applies exclusively to disk-based backups. Those will include data domain, MSDP pools, advanced disk, and basic disk. Does not apply to tape. The file above that, size data buffers, applies only to tape. It doesn't apply to disk. So these two don't affect each other, but they do apply to the appropriate naming. So anything that does not have the underscore disk applies exclusively to tape. Then we have number data buffers and number data buffers disk. And again, this is going to be if there's no tape on the end, but it does apply only to tape. And this is the number of buffers to create, and the same for disk. In older versions of NetBackup, you also had the touch file for NetBuffer SZ, and this is the network buffer size. That is now, for the most part, auto-tuned and will adjust dynamically based on the network settings and the capabilities of the network. And lastly, we have the no SHM file, which is used to bypass buffers and to move data directly. For a client side, we don't have a touch file. We have a setting within the client, communication buffers. And this is a setting that controls how large of a block of data do we send across the network. And we'll cover some of the values that can be set here, as well as how to tell what to set here. So next we'll move on to where are these files located. So for the media server side of it, we're talking about size data buffers and size data buffers disk. In Windows, those are going to be under the NetBackup DB config. And for non-Windows, those will be under the NetBackup DB config under user OpenV. These files are case sensitive and they cannot have an extension for both Windows and for non-Windows. They need to just have the file name as you see it on the screen here. And this applies as well for the number of data buffers, which are in the same folder. For the no SHM, it's slightly different. This is going to reside on non-Windows under user OpenV NetBackup, and for Windows under the NetBackup path. And again, these are in uppercase with no extension. For Windows files, by default, when you install a Windows operating system, it's not going to show you the extension, and so you'll need to make that adjustment in your Windows Explorer. So you'll want to go to the View setting, and you'll want to show files and folders, and you'll also want to uncheck the option to hide the protected operating system files, and check the option to show extensions. So otherwise, when you create the file, the extension won't show, but it'll actually have that extension hidden. So it's the option is in this box here, and you can get to that by showing your toolbar in Windows Explorer, going to Tools, and choosing Folder Options. Once you've set the value, you'll click the Apply to Folders. This applies it across all folders. So let's move into what to tune and how to know what to tune. This is probably the biggest part. And there's a lot of articles that cover this, but I'd like to try and cover today what we leverage most often. So the biggest indicator, of course, we discussed it early on, was the slow backups. One of the ways you can see that in your jobs is to look at the job details. And in this example here, your wait cycles, you'll see that the number of wait cycles are very high. So when you're looking at the job details, you're going to see waited for full buffer, and it'll give you a number. In this case, it'll give you 2428, and it tells you it's delayed a certain number of times. So what this is saying is that it's waiting for data to go out to the disk, but it doesn't have a full buffer to take, so it has to go into a wait cycle. And these are reported in at the end of the job. So once the job is completed data, it'll report the number of times it waited for full buffer or waited for empty buffer, and then you can make your adjustments appropriately. One thing to note here is it's near impossible to tune out all of the delay. The goal would be to make your adjustments to get these delays to as minimum as possible to improve your performance. So how do we know what to change? So waited for full buffers. This means that the BPTM write process went to take a buffer of data, but there were no full buffers, and so it has to go into a wait cycle. So this is the process going to write out to either disk or tape, and it goes to grab a block of data, but it doesn't have a full block. So it has to go into a wait cycle and check back. Do you have a full block of data now? Okay, I can move. This cycle is 10 milliseconds. It doesn't seem like a whole lot, but these start to add up rather quickly, especially when you start to get into tens of thousands or even hundreds of thousands or higher. These delays will add up quickly. The alternative to that is waited for empty buffers. And this means that the client had data to send over, but there was no room to store it. These buffers are stored into memory, and we'll dig into that in an upcoming slide here. We're really going to dig into that a lot deeper. So the client had data to send, but there was nowhere to put it. The storage is busy. The buffers are full. And again, it's very difficult to tune out all of the delay. The idea is to get it as low as possible. The key to tuning this value is to determine the time spent in these delays. So a write delay is 15 milliseconds, a read delay is 10 milliseconds, and these add up based on whether you're waiting for a full buffer or waiting for an empty buffer. You'll need to compare these values to the job runtime. And what we mean by that is if you have a job that is running for 20 minutes and you're taking a large number of delays, 20,000, 30,000 delays, that's a significant amount of the overall job time spent waiting. For those same number of delays, say 10,000 to 15,000 on a job that's maybe been running for 18 hours, that's not a significant amount of time, and so you may find that you may not be able to tune that all the way out. The key is to determine how low can you get those values and to judge the amount of impact that these delays are having on your job. So let's find out how we can determine what settings are in place. The default settings are a 64K block size. That is for both disk and tape. And that will be represented in bytes. And the number you'll see is 65536. These are reported every time a job starts. So when you look at your job details, and you'll see in this example here that the job has started up and it's telling you that it's using, in this case here, it's a 1 meg buffer size. And then it's going to tell you how many of those buffers it's going to use. So every job will report that. So you can see here we're using 128 buffers and they're 1 meg each. So we'll talk about the acceptable values. These numbers have to be in a standard block size. So for the size data buffers, the size has to be in multiples of 1024, and the acceptable values are listed below there, 32768, and it's basically double it each time to give you your block size. With the size data buffers, there's a couple of gotchas you need to be sure to test because the size data buffers applies to tape only. And using this value requires that the tape drive supports the block size that you're giving it, that the cards that are using the HBA cards support that block size, as well as the operating system. So this will require a little bit of research. You'll need to determine, does my operating system support a 512K block? Does the tape drive support that? Does the HBA support that? So that involves a little bit of research. Anytime you change this value, you should do a test of a backup and a restore to make sure that your data is accessible. Another important note on this one with tape, if you're changing this value, what this does is this changes the block size written to a tape. So a tape that was written with default value of 64K is writing 64K blocks to a tape. If you change this value and attempt to write to that same tape that has previous data written to it, you'll get a media write error because the block size, you're feeding it a 256K block, but the tape is formatted 64K, and so it will fail. You'll get a status 84 on that. So what I usually recommend in this instance is to note the date that you're making the changeover for two reasons. One is that tapes that were written to prior to that are assigned and have data on them will not be able to be used for further backups. And two, when you attempt to do a restore, you need to know what block size the backup was written with. So if you change that value, let's say on August 1st, you'll need to know that anything prior to August 1st has to be, the block size has to be whatever the value was prior to then. Anything going forward uses the new block size for restore, and you'll adjust the size data buffers to match that. If you don't do that, you will get an error in NetBackup. It's not very clear, but you will get a media read or media write failure if you're attempting to write to a tape that was a different block size. The number of data buffers does not have that limitation. This can be adjusted on the fly. And changing this value just increases the number of buffers. It does not have any impact on restore. So you can change that between jobs. One thing to note here is that once a job starts, in the job details you see that it's allocated 64 buffers. Increasing that number does not change the job. The job has already got its values and it will continue to use those. The next job that runs, when it starts up and reads those files, will then apply those changes. And the acceptable values here are 16, 32, 64. And a lot of these numbers are very common, so those are all listed here. When you're creating these buffers, you need to be aware of the RAM limitations of the machine. So if you have a server that has 4 gigabytes of RAM, you need to be aware if you're creating 1 meg buffers and you're creating 512 of them, every job is going to attempt to use 512 megs of RAM. So you're going to be limited to 8 jobs will take up that 4 gig of RAM. You can swap, but that leads to some severe performance issues, and I will cover that in an upcoming slide as well. For disk-based backups, you'll use the size data buffers disk. Veritas has a canned number that they recommend using. They recommend using a 1 meg buffer, and that's represented by having the file size data buffer disk and having a value of 104.8576 set in that file. When you enter these values in a file, you'll want to make sure that you don't have any carriage returns or extra characters. It should only be the number in the file. This Veritas article actually covers this touch file and the recommended value here. Corresponding with the size data buffers disk is going to be the number data buffers disk. So it'll have an underscore disk at the end of that. These values are the same. It's the 16, 32, 64, 128, etc. These are all in RAM, so you'll want to take into account the number of jobs you're going to run, the amount of RAM in the system, and you'll want to, of course, leave room for other processes and other things going on in the server, including the operating system. So it's important to make sure not to exceed the amount of RAM in the system. So now we'll get into how these work, and this will kind of help put it together a bit better. And we're going to get into how the buffers are used. So when data is being moved from a client to a storage unit, there's always going to be a data path that will be capable of varying speeds. And you use your buffers to offset the stop and go. You try to make data move as smoothly as possible so that nobody's waiting for data. So the goal of buffers is to provide a bucket to collect the data and allow NetBackup to compensate for the varying speeds. So when a job starts up, it's going to read these values and set them, and it's going to create these buffers in memory. The goal of the buffers is to create data reserves so that the process writing out to the storage unit never has to wait for data, while at the same time, a client providing data never has to wait for room to put that data in. So on this slide here, we kind of have a graphical representation of how data moves. So down here at the bottom, you'll see this is the client data. So you have a client out there that's backing up, and you have the BPB car process that's reading data, and it's prepping the data into blocks and sending it across to the media server's BPTM read process, which puts it in the buffer. On the other side of that buffer is a BPTM write process that is taking data out of that buffer and writing it to the storage unit. The idea here is that your buffers are large enough that neither side has to wait for data. It's important to note here that BPTM cannot take a partial buffer unless it's the last block of data. So if your buffer size is set to 1 megabyte, the BPTM process can't take 512K, it can't take 768K. It has to have a full 1 meg buffer before it can take that buffer and write it out to disk. The only exception to that is the last block of data from the backup, and that's simply because it's not always going to be a full megabyte. So that's an important note there. So let's move into the client-side tuning. And this is the client communications buffer. So this determines the block size of data that's going to be sent across to the media server. This is really a balancing act, and it requires some knowledge of what type of data is on your client, including specifically the file size. So the first thing to look at here is what are the typical files that you're storing on the server. In the case of having a file server that maybe stores a large number of videos, a larger client communication buffer size is going to benefit your performance if the majority of the files are larger. If the files are smaller, say they're 1K text files or 2K text files, decreasing that client communication buffer is going to be more efficient. And the reason behind that is that if you have, in this example here, if you have primarily large files, video files, and they're 5 gigabyte, if your client communication buffer is really small, the file has to be broken up into that. So let's say you set an 8K client communication buffer. That 5 gig file has to be broken up into 8K chunks, which is a large number. And once it has 8K, it can send it across the network. For very large files, and the majority of the files being that way, that's going to be a very intensive process. So increasing the client communication buffer to, say, 128 or even 256 is going to significantly improve your performance. That's a lot less chunks of data, and they're being sent over. On the opposite side of that, if you have very small files and you have a large communication buffer, this is where you'll really see the performance drop. So in an instance where you have the majority of your files are 5K or less and you have a client communication buffer of, let's say, 256, you have to gather up a large number of files to create that 256K chunk of data and then send it across. And this creates a large amount of overhead on the processor and RAM, as well as a delay while all the disk reads are performed and all the data is gathered and then it's sent across. So that can cause a significant performance hit. So in those situations, it's best to lower that client communication buffer size. And this is one of those things that you can adjust, and you'll lower the value and see, does your performance improve? If so, maybe try lowering it further and see what your impact is. So this is kind of one of those things there's no exact methodology for, but you'll try to adjust it to the best performance, and there'll come a point where once you've done it too far, you'll see the performance start to turn around and start to lower, so then you'll go back to where you were, and that's going to be your best spot. So let's move into multiplexing and multistreaming, and this is exclusively for tape, for the multiplexing side of it. And so multiplexing is combining streams of data into a single stream to go out to tape. This is a great way to push your tape drives to make sure that they, as the newer generations of tape can move a lot more data, write a lot more data a lot faster. A single stream from an older client may not be sufficient to keep that tape drive moving. And so what you'll want to do is you want to send more data to it. And the way you can accomplish that is to have multiple clients sending multiple streams and combine those streams to one tape drive. This avoids what's called shining. If you have a client that's not able to provide data fast enough to a tape drive, the tape drive will receive the block of data, write the block of data, and then it's going to be waiting for the next block of data. At that point, the tape drive has to back up and then reposition again for the next block of data. So you want to keep that tape drive constantly streaming data. In the illustration here, you can see we'll have 5 different clients, and based on the client's capabilities, the connectivity, you can send multiple streams from a single client. As we see in client 1, we're sending 2 streams of data. This is going to generate 2 different jobs in NetBackup. Those will be put into a multiplex group, and based on the settings you set for your tape drive and the number of multiplex streams, we'll combine them into a single stream out to your tape drive. There are some downsides to using this. One of them is that it does slow down restores. And this is simply due to you have multiple backup images going to a tape drive, and it's writing the blocks as it's receiving them. So it may take a block from client 1, a block from client 3, a block from client 5. So reassembling the image for a restore takes a little bit more time. So that's one of the impacts. The other impact is also going to impact duplication of tape, because of the same reason you're going to be pulling an image out. Unless you preserve multiplexing, you have to gather all the blocks for a specific image, which may be scattered across the tape. So this does impact your performance. Ideally, when you're setting up multiplexing, you should start with a smaller number of streams to your tape drive and work your way up to find what is going to give you the best performance. And you need to take into account the number of streams and their performance combined together. You'll want to look at your tape drive performance. How busy is the tape drive? How much data is it ingesting? And you don't want to go to and send too much data, because then what you end up doing is introducing delays while it's waiting for data to be written out. So this is one of those things you kind of start with a smaller number and move up. Typically you want to start with 2 to 4 streams, and you don't want to go any higher than, say, 8 streams of data. So the good spot is going to typically be between 2 and 8 streams. This involves a lot of performance monitoring of your tape drive, as well as your media server, to see what its capabilities are. Next, we have multi-streaming, and using this image below, you can see we have client 1 has multiple streams. It has 2 streams going out. Client 2 will have 3 streams going out. This really comes down to the capabilities of the client itself. Older clients may not have the processing power of the memory or even disk capability to send multiple streams of data, and sending too many streams of data will actually negatively impact performance. There are a couple ways this can negatively impact performance. If you send too many streams of data, for example, an older client that you maybe try to stream 8 streams of data, depending upon the source of those of those streams can cause the client to be unavailable on the network for, if it's a file server, it may become very slow. It also can cause what's called disk thrashing, which is if you have 4 streams of data coming off of a single disk, that can cause that disk's I/O not to be able to keep up, and so it's grabbing a block of data for one stream and then for another stream, so it's chasing all over the disk trying to gather the data as fast as possible, and this will cause your backups to slow down. So this is heavily dependent upon the client's capabilities. So now let's move into some of the appliance stuff. As appliances have become more and more popular, they're a great solution. One machine or server in your environment has your storage, it has NetBackup in it, it's got the operating system, and it's basically you're going to plug it in and ready to go. So as these become more popular, some of the tuning that goes with it changes a little bit from traditional NetBackup. We now have an operating system that is supplied with these appliances, and there's some considerations with that. At the OS level, use tools like TOP to take a look at your memory usage. One of the keys with appliances as well as traditional servers is to avoid using swap as much as possible. If you find that you are opening up TOP on an appliance and the swap usage is extremely high, reach out to support and we can help you look at that. There's a lot of different ways that that can be addressed, but it's one of these things where we need to look into what is using the memory and how can we adjust it. One of the big things you'll find is if you adjust your buffers, the number of buffers and size of buffers too high, this will lead to swapping. And so if you have going outside of a normal, if you have 1 meg buffers and you do 1,024 buffers, that's going to be 1 gig per job. For an older appliance with 128 gigs of RAM and it has the MSDP pool attached to it, if you start to run, say, 80 streams, that's 80 gigs just for the streams. Add in the operating system, NetBackup itself, MSDP pool management, and now you're going to get into swapping. The reason swapping is going to cause such issue is you want that data to be basically brought in from the client and written out to the storage unit as quickly as possible without having a lot of stops along the way. When you're swapping data, what's happening is that the processors, the data is not getting moved. It's waiting on something. So what happens is RAM gets full. When RAM gets full, data is taken out of RAM, written to disk. Once that block is written to disk and it comes up to be processed, everything has to go into a wait cycle, read the block back out of disk, put it back into memory, process it, and then move on. This causes a massive delay, so you want to avoid that as much as possible. Your size data buffers and number of data buffers are key here. If you're using those tuned values, you can look at ways to lower that, but I would recommend contacting support. We can help you work through that. On the NetBackup side of things, the biggest issue that we've seen lately has been with policy execution. It's important to stagger your backups starting. With the number of clients that NetBackup is capable of backing up increasing, the amount of data increasing, the amount of load that's required, or the amount of resources required to process these jobs goes up. One of the ways you can alleviate the load on that backup is to stagger your policy start time. So having 100 policies kick off at 5 p.m. is a heavy load. So NetBackup has to read through each one of those policies, allocate resources for the number of clients, the number of streams, the tape drives involved, if any of those are involved, the media server, and all those resources have to be allocated at one time. And that can create a significant load at that 5 o'clock window. Ideally, you stagger those policies by 30 minutes, so you maybe kick off 50 of those at 5 o'clock and 50 of those at 5:30, and this really lightens the load on resource allocation, and your jobs overall will perform better because resources will be more available to those jobs. Another thing to look at is your policy update interval, and this is how often your policies are read through and evaluated to see if they're due to run, and this is based on the scheduled time. By default, this is 10 minutes. If you have a large number of policies, and by large number that will typically be over 100 to 200 policies, you may want to consider changing this value and increasing it to 15 to 20 minutes. If your policy number is even higher, 350 to 500 policies, it will help you significantly to change that interval to 20 to 30 minutes. And this is simply how often a policy is read in to determine if it's going to run. It's not going to impact the job start time. It may cause the job to start 5 minutes later, but it's really not going to impact that big of a deal. One of the biggest things that I have seen with disk pools, this is a big one I've seen as well, is disk pools and their credentials. In the example we see here off to the right-hand side, you'll see we have 5 media servers, each with their own disk pool. By default, when a media server is added in, the credentials are created when the disk pool is created. You can have each media server have access to each disk pool. And in this example here, so we simply have 5 media servers with 5 disk pools, each media server having access to each disk pool. So media server 1 has access to all 5 of these disk pools and has the credentials to access each one of those disk pools. And as you can see by the diagram, it gets quite complex the more media servers having access to the disk pools. And what happens is each one of these connections has to happen to verify that the disk is alive. And this is called disk polling. So media server 1 has to check with each one of these disk pools to make sure it's still there and responding. As you increase the number of disk pools in media servers, that amount of crosstalk starts to become a problem when the disk pool is ingesting data. So you have backups running, and now you also have to do this disk polling, which happens every 5 minutes by default. This really starts to cause a problem with disk pools going down. In several examples I've seen, a local media server is writing a backup to its disk pool, and the disk pool gets marked down in NetBackup, but the backup that is running at that time continues to write. And that's simply because in this example, let's say media server 1 is writing to its local disk pool, so write MSDP1. Well, media server 4 goes to poll MSDP1, but because it's ingesting data and it's very busy and the other media servers are also polling it, it takes a long time to respond to media server 4. So media server 4 will report to the master server, hey, I can't reach this disk pool, and NetBackup will mark it down. So what you can do to alleviate this is to control the access that the media servers have to a disk pool. If media server 1 is only going to be writing to MSDP1 and maybe MSDP2, there's no reason for it to have credentials 2, 3, 4, and 5 if it doesn't need to read or write from that disk pool. So unchecking that from the disk pool will limit its ability to talk to those disk pools and limit its need to poll it. It won't need to poll the disk pool, and that's done under credentials. So that will significantly improve response time of disk pools and will limit the number of 2074 errors or disk pool down warnings. That's typically going to reduce that, and that's one of the things I would look at first. SLP processing is another point that performance will rear its head. If you have a very large backup of SLPs, this causes the SLP manager to have to read through that list to build its batch of duplication images. When you're implementing SLPs, one of the best things you can do is to slowly integrate your SLPs. Set up an SLP, move a couple of your policies over to that SLP and monitor it to make sure that your backlog is not increasing and that your link is capable of supporting the data movement. So you may want to create 1 or 2 SLPs, monitor them for a couple of days and make sure that all the duplications and all the SLP processing is happening within a 24-hour span so that the next batch of backups doesn't add to that list, that each day it keeps up. And this is one of the key parts, is to slowly integrate these so that you don't build up a very large backlog. The second consideration with SLPs is the direction. And in this example here, we have 100 incoming backup streams. So we have a media server that is writing out 100 streams of data to an MSDP pool. And then we try to add in 50 outgoing SLPs to replicate data out of, either replicate or duplicate data out of an MSDP pool to maybe to tape or to another MSDP pool. Now what we'll have is 150 streams of data trying to move 100 in and 50 out. And this causes the disks to have to read and write data, and this introduces a large number of delays. So you can use your SLP windows to help control that and try to keep data moving in the same direction. This will help significantly improve performance. One of the biggest things that you'll find is when you make adjustments to this, if you have backups going and duplications coming out of there, the amount of data is going to remain constant. In other words, you have a certain amount of data that has to be written in, and you have a certain amount that has to be duplicated out. Having them happen at the same time, switching between reading and writing, hurts both sides. A lot of times we'll see a significant gain in letting backups run. The performance of backups will go up significantly, and those backups will complete sooner, and then the duplications out will be just reading data out of there, and those will run a lot faster. But mixing the two impacts both of them. So you'll gain a lot by making sure that your data is moving in the same direction as much as possible. Another performance point on appliances is mixing data types. With MSDP pools, their deduplication engine will break up the data and match the data to see if the block exists on storage. The basis of deduplication is not to write the same block of data twice, to simply use pointers. Having different types of data decreases the efficiency of MSDP to store data. For example, having Oracle, VMware, and NDMP backups all going to the same MSDP pool will significantly impact deduplication performance, both in the speed that data is written as well as the deduplication rates. So deduplication rates will drop significantly when you mix more data types in, and that's simply because the data is always going to be different between different types of backups. So this will cause the deduplication rates to drop. The deduplication rates are going to drop, and this is simply because we're having to write more blocks of data, which increases the load on the CPU and RAM. One of the ways you can offset this and other performance issues as well is to leverage an advanced disk if this is possible. One of the things that you can do is if you have data that is going to be destined for tape as well as MSDP pool, either with the same or different retentions, is to write it to an advanced disk, and then from that advanced disk, duplicate it out to MSDP and to tape, and have the original image on advanced disk expire after the SLP processing is complete. This really will increase performance since we don't have to deduplicate the data to the MSDP pool, then rehydrate the data to put it out to tape. This will gain significant performance. Any of those duplications, so if you write it to advanced disk and then you duplicate out to your MSDP pool and to tape, you're not touching that client. So you get the data from the client really fast, write it out to your advanced disk. There's no deduplication, no overhead of the deduplication fingerprinting and all that. Then you can duplicate it out and not have to touch that client. It really helps a lot. Another thing that can impact performance will be the MSDP maintenance. So when you're using an MSDP pool, there's a lot of maintenance that has to happen in the background, and these are scheduled to happen twice daily. The biggest ones are compaction, CRC check, and rebasing, and these are all to keep the MSDP pool as efficiently as possible. Compaction helps to combine the segments of data to use less blocks, which frees up those blocks instead of having the blocks on the disk half used in the majority of the disk. These are combined to make more efficient use of the blocks, which frees up space. CRC checking is simply checking the blocks of data that they are readable and that the data checksum matches what it should be. And then rebasing is the organization of the databases that manage the MSDP fingerprints. You can improve performance by disabling these processes for a short term, and by that you would want to maybe disable them during the middle of your backup window. So if these are scheduled by default to run at 12:30 a.m. and 12:30 p.m., if 12:30 a.m. happens to be when the majority of your backups are running and you can't alter that, you may want to consider turning off the compaction, CRC check, and rebasing, and then turn them back on at, say, 3 a.m. to allow them to run under the normal schedule. It's not recommended to turn those off permanently. Any more than 24 hours can significantly impact the MSDP pool's performance and put your data at risk. Not doing a CRC check, it has no way of verifying that the blocks of data are restorable, so this is not a recommended method permanently. This does help get you through certain windows, but you should always look to try and avoid those windows with your most intense backup load. So now the considerations, and we've kind of touched on these throughout the presentation, but I wanted to centralize these here and have this page to kind of cover those. The biggest one being server memory, and the biggest culprit here is allocating too many buffers for the amount of RAM in a server. It is always important to consider the amount of RAM and the number of streams that are being moved, whether it's backup or duplication. It's always important to know how many streams under peak load, what are you looking at? So if we go with some easy numbers and say 100 streams of data at your peak load, if you have 512 1 meg buffers, so you have 512 megs per job, and you have 100 jobs, you need to have the RAM to support that. So in this example here, we have 512 1 meg buffers. They're going to use 512 megs per job. 32 jobs is going to use 16 gigs of RAM for buffering. If your server only has 12 gig or 8 gig, this is going to result in moving into swap, and the performance going into swap is going to be very bad. So it's best to consider to stay under your RAM usage. Your job individually will perform significantly better and will get out of the way sooner for the next job to jump in. So it's not always about the number of streams of data, but how fast the data is moving through. That's one way to look at it. So if you have jobs that are moving through at 100 megs a second, and you're moving 10 jobs, so you're moving a gig per second, that performance is pretty good. But if you start to increase the number of jobs, you're going to decrease the speed of each job for every additional job, and you reach a point where your jobs are fighting for resources, the performance drops, and you're not moving as much data, because it's all about how much data are you moving at a given time, not the number of jobs. I wanted to hit upon this point again as well. Changing the size data buffers changes the block size written to tape and can cause media issues such as restore failures and media being frozen. When a tape is allocated in NetBackup, the size data buffer is what the tape is formatted to when the data is being written to the tape. So if you use the default setting on a media server of 64K, the block size written to tape is 64K. If you increase the value to 128K, when it goes to write to tape, the first 64K of the block will write, but the tape drive is going to report an end of block. And NetBackup is going to say, well, I've got 64 more K that I should be able to write here, and that's when you're going to get a media write error. So it's important to note that time that you make the change. Mark it that, on August 1st, we changed from 64K to 128K. And that way for restores as well as for tape usage, because you are going to have tapes that are not going to be able to be written to until all the data on that tape has expired and it becomes scratch again. When that happens, the tape will be reformatted on the fly when you write your backup. And again, hardware support is important when it comes to this value for tape. And I do want to point out this does not happen with disk. Since disk block sizes, there is an extra layer in there with the operating system writing out to blocks, and it can simply move on to a new block. You can't do that with tape. So this does not impact disk-based backups. This is only for tape. So you need to consider what is the maximum block size that the operating system, HBA, and tape drive support. Server and client memory. When we adjust the client communication buffer size, we're increasing the amount of memory that the client is going to use per stream, as well as adding multiple streams of data from the client also increases the memory usage. For example, if you have an older Windows 2003 client and you try to send 32 streams of data, 32 streams off of a client, that's a significant load on what might be an older piece of hardware and is an older operating system. That's a significant amount of resources, and that may make the server not be able to serve files or whatever its main role is. And so this is a consideration you'll want to take into account. And one good way to look at this is under peak load when you're running your backups is to log into the client, take a look at its memory utilization, its processor utilization, disk utilization, as well as network utilization, to make sure that if this server has a role of being a file server, that it's capable of serving files to its clients, and that backup is not taking that role away by using all the resources. Another important point is the multiplexing, is to make sure that you do not overwhelm a tape drive by sending too many streams, and that goes along with starting at a lower number and gradually increasing the number of multiplex streams you send to a single tape drive. Ideally, you want that tape drive just spooling through and not having to stop and reposition, so you want to send as much data as the tape can handle and try to keep that tape busy. We covered the buffers and waiting for empty buffers versus waiting for full buffers. And those details are they'll show up in the job, and you can determine which way you need to adjust. So let's move into some testing and to help you determine where to make your tuning adjustments. In older versions of NetBackup, this was accomplished through what's known as BPB-CAR to null testing, which is basically having the client process read the data that's to be backed up as fast as possible, but sending it to null. So it's not actually transmitting it across the network or sending it out to any form of storage. It's just reading it as fast as possible. This helps identify what might be client-side issues. It helps you determine if your disks are capable of supporting the transfer speeds that you'd expect to see. This is one good way to get an idea of what your client can do. Select a directory or a drive, run the test, and see how quickly it processes the data. And you can look in the log, turn up your logging, and see what you find in the log. There's a couple of different entries based on the operating system. So for non-Windows, the default path is user openv NetBackup bin BPB-CAR, and this is the command line you'll use, and this is available in the presentation as well. So this is the command line you'll use. It's BPB-CAR, no cont, and the critical part to this is the file system that you're going to tell it where you're going to, what folder you're going to use to run this test. On Windows, you'll see the X:\/ is the path to backup. Then you'll review the amount of data versus the time it ran and determine what your throughput is. And that gives you an idea of how fast can the data be written from disk. Another method in the newer versions of NetBackup is called Gen Data, and there are a couple of articles here that will walk you through how to perform Gen Data testing. And this is basically a more end-to-end testing. It's going to give you the ability to read from the client, send it across to the media server. So in the case where a BPB card's a null, tells you your disk performance is good, then you need to look in other locations for your bottleneck. These articles will help significantly with that. The last test you also can use is NB-PerfCheck. Now this is a tool used more toward OST devices such as Quantum, DXIs, or data domains that are used as storage. And this tool will test the ability to send data to the device and how quickly does it ingest data. And I've included some articles that include the download for the utility as well as how to use it. And there's an MSDP specific article for the media server deduplication built into NetBackup. Some common issues. This is something we've covered throughout the presentation here. Creating too many buffers increases memory usage. Changing the buffer size and not tracking the change can result in restore issues. And here the media write message was one I wanted to point out. And in the older versions of NetBackup, it was not able to compensate for a block size change that was too large to be supported by hardware, and it would actually fail the job with a media write error 84. In new versions of NetBackup, it will simply revert back to the default. And this is a typo here, but it should be 65536, 64K, the default. One additional item is a NetBackup console that's slow. This is a big one as well. Use the command nb-emm-cmd list host and look for invalid servers. And these are media servers that may have been shut down but not properly decommissioned within NetBackup. Since they are in EMM and part of NetBackup, it will try to poll them to get status of disk pools, status of the server itself. And this causes a significant delay, especially if that number gets to be 5 or larger. This will cause some severe impact in moving around the NetBackup admin console, as well as job performance, and it will also cause issues when trying to administer NetBackup, such as adding credentials, removing credentials, things like that. You'll start to see timeouts. So use nb-emm command delete host to remove invalid servers, or nb decommission. I do want to point out that with nb decommission, there is a defect against that, and you should be aware of that. So before using nb decommission, make sure you check the Veritas site that your version is not impacted by that. The 8.0 version of NetBackup or appliance code 3.0 does not have a defect for that, so you are safe to use that. But older versions of NetBackup that are no longer supported, that have reached end of life, still do have this defect. There is a patch for it on the Veritas site. That is the material I have for today. I see that the questions have been answered. That's good. If you do have feedback or additional questions that come up, please do feel free to reach out to support, and we will answer those questions for you. With that, I will turn that back over to you, Amanda. Thank you very much for your time, everyone.
Thank you, Chette. Thank you for attending today's webcast. An on-demand version of this webcast will be available within 2 to 3 days of the webcast. You will receive an email notification once the recording is available. Thank you again for participating in today's webcast. Have a great day.